Okie we had this magnificent induced magnetic field last time. Now we want to know a little bit more about it. What are its repercussions? What does it do? Sorry, I was just checking what time we were looking to be finishing, and we're aiming to finish at 3:45, so we've got plenty of time. Good, right. Faraday's law and Lenz's law are easy to combine, but we'll tackle them one at a time, and then I will show you why they're easy to combine. Faraday's law states that the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. Okay, so I've got an EMF is directly proportional to the rate of change of magnetic flux linkage. So that is, I had two symbols looking like this, and I had one that was kind of shorter and looked a bit more bold. That's the rate of change with respect to time. Magnetic flux linkage, if you recall, was just magnetic flux multiplied by the number of turns in the coil. And magnetic flux itself was the magnetic field, the magnetic flux density multiplied by the area used to try and sort of catch those field lines, multiplied by the angle between the normal to the area and the field lines. Okay? You could then ask yourself, when you have a specific question, which of these n, b, a, cosine theta, are any of these going to change with respect to time? N is unlikely to. It would mean that your coil itself was kind of unraveling or getting more turns. B might change if you've got a sort of varying magnetic fields, but unlikely. A, also unlikely to vary unless your coil is sort of rearranging itself to get wider. Most of the time, the change with respect to time will be in the angle. Your coil will be spinning, or perhaps, waggling side to side. You can also get changes in the field strength. For example, if you have a coil and a permanent magnet, and you move the permanent magnet closer and further apart, the field strength will get stronger as the permanent magnet approaches. So it'll basically just be those two that it might change. If either of those two do change, an EMF will be induced. Great. And Faraday's law tells you how to calculate size of that. Lenz's law tells us what the effect of that EMF will be. Lenz's law says that the direction of the EMF will be induced in such a way as to produce a magnetic field which opposes the motion inducing it. Okay, so if I have, we'll get to a diagram on the next slide. The mathematical statement of Lenz's law is actually just, I don't know, it almost seems a little stupid. Here's Faraday's law. Lenz's contribution is putting a minus sign out front, just to say, look, it's going to oppose whatever the field is that originally caused all this. But hey, it's a pretty neat physical insight. It's just got a slightly goofy mathematical resolution. Lenz's law is a consequence of energy conservation. What do we mean by that? Well, I distinctly remember my physics teacher saying this to me actually. Imagine the alternative. So if you moved a magnet, you did some work moving a magnet towards a coil, and it, in turn, an EMF was induced in the coil and a current ran, and that would cause its own magnetic field. And instead of opposing the motion of you moving the magnet, instead it encouraged the motion. You'd have the situation where you basically do a little bit of work moving a magnet closer to a coil. It then gets kind of sucked into the coil because the magnetic field produced by the coil agrees or sort of welcomes the change of your permanent magnet moving closer. And you've essentially invented a perpetual motion machine. Just one little start, and then it gets converted into kinetic energy, just like that. Yeah, and so to preserve energy, because you're storing energy in the magnetic fields that you create, you need to have a force to work against when you are pushing your permanent magnet closer to your coil, and the resistance to that motion comes from the induced magnetic fields. If it didn't resist the approach of the permanent magnet, then you'd essentially be creating a magnetic field out of nothing, out of no energetic, out of no work done, and that would be naughty. Basically, you'd be creating energy out of nothing. Okay, moving the north pole of a magnet towards a coil produces a current. Yep, and it will be induced. Which way will it be induced? Again, we'll fall back on our right-hand grip rule. It will be induced in a way such that the north pole, my thumb, must make this end into a north pole, because that's what's going to reject our approaching magnet. Okay, therefore I know the current goes around this way. And it goes. The induced field repels the movement of the permanent magnet, and this is Lenz's law in action. So I've just got something written on my notes, but I just can't read it. Oh, I see. It's just saying this is the induced field. Okay. And that induced field will itself disrupt the original field, the pink one. Okay. But you say, fine. If you don't like the approach of my permanent magnet, I'll take it out. But as soon as you do that, Lenz's law says that the EMF induced in this coil is going to oppose whatever motion causes it. And so if you're trying to remove your permanent magnet, the direction of the current, the direction of the EMF induced, will reverse, such that this is now a south pole and attracts your permanent magnet. So you can see between these that suddenly the south pole, so the north pole needs to be this end, and so the direction of current reverses. Here it was going left to right, now it's going right to left. So it's very indecisive, the induced magnetic field. It's saying no, don't go. Basically just wants everything to stay still. It is the ultimate small c conservative force. It just wants everything to stop. Everybody stop making such a ruckus. This induced field attracts the permanent magnet. It certainly does. The current always flows anti-clockwise around the North Pole. Yeah, that's worth just pointing out. So if I was an eyewitness at sort of looking at this from this end, what would I see? I'd see the coil as a circle, and this is the North Pole, and the current always flows anti-clockwise. So it always flows that direction. The way people help, try and remember this, it's like the letter N itself kind of suggests a certain anti-clockwise motion. Okay. Right. Let's have a look at this exam question. Before we do, I'm just going to take a quick look ahead, see roughly how much we've got to cover. You know what? I actually think we're going to be perfectly fine for time. If anything, we might have a little too much, so maybe we'll be able to have a slightly longer break at the next opportunity. Right, a wire coils around an iron core, is held in a magnetic field whose magnetic flux density is increasing at a constant rate k. How interesting. State with a reason the relationship between k and the EMF E induced in the coil. Okay, it's a state question, but not necessarily an easy one. A second core is moved away from the north pole of the magnet. State the direction of the current induced in the coil and why it's in this direction. Okay, the first one is asking for a mathematical relationship between. Okay, let's tackle that one first. Okay, so for 1 mark, the EMF induced, we know, is the rate of change of the magnetic flux linkage, and the flux is itself, N, B, A, cos theta, blah, 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 blah. Okay, so are any of these changing? No, these 4 aren't, because it's the wire coiled around an iron core. It's held in a magnetic field, so it's stationary. But the magnetic flux density is increasing. We are essentially being told that B is, dB by dt is k. The rate of change of B is k. And so if I differentiate, if I look what is changing with respect to time, all of these we can chuck outside our expression, and B will be differentiated into k. I know not all of you do A-level maths, but hopefully you realize that the rate of change of B is the only thing that's changing, and that rate of change is just equal to k. Therefore, tracing back up here, epsilon is simply proportional to k. 1 mark for stating that. I think that's actually a little bit stingy, because it requires a bit of mathematical thinking. What does it say? State with a reason, though. Haha. Okay, so there's a second mark to be had. The reason is exactly what I've actually already worked out there. By Lenz's law, you get d theta by dt, and the rate of increase for the magnetic flux density, but that obviously is part of the magnetic flux, is k. Okie dokie. The second question. A second coil is moved away from the north pole of a magnet. State the direction of the current induced in the coil and why it is in this direction. Current will move. Yeah, this is a little awkward. So you've got a coil, blah, 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 blah. And then you've got this magnet that is being moved away from the north pole of the magnet. So this whole assembly is moving. Then you have to describe what way is the current flowing. Well, it's going round in a loop. The way we've answered this is actually a pretty good one. So the current will move clockwise as viewed from the north pole, the furthest pole. Yeah. So we're sort of looking at it from here. Lenz's law will act such that the current induced will make a magnetic field that will mean that the south pole is here and the north pole is here. Why? Because the south pole will attract this fixed north pole, and so it will oppose the motion that's causing it. We said that if we were looking at a north pole, the current would flow anti-clockwise, Therefore, if we're looking at a south pole, it will be going clockwise. Okay. Why? Okay, because of Lenz's law, the magnetic field induced by the current will oppose the change causing it. In this case, the field that's causing it is the permanent magnet. The induced field will attract the magnet to oppose the motion of the magnet moving away from it. Yep. I believe, by the way, in your booklets, I don't think it has this phrase as viewed from. So whatever it says in your booklets, feel free to amend it if that would make you feel like it makes more sense. Current move clockwise from north, whatever it says in your booklets. I don't have a copy to hand, I don't think. Right. Yeah, well, here's the diagram of what it would look like. It would be going clockwise from this perspective. So this is indeed the south pole, this is the north pole. And our induced field would look a little bit like that.